So lesson 3 is going to be on anhydrates and hydrates. We're going to be talking about anhydrates and hydrates, prefixes for water molecules, hydrate to anhydrates, which is just a water loss calculation, and then percent composition of these hydrates. So an anhydrate is an ionic compound that does not contain water trapped in its crystal lattice. Think of it as being dry, anhydrous, without water. Water gets trapped into these crystal lattices because they have these open spaces between their atoms. So water molecules are able to get trapped inside. Water molecules, remember, polar bonds, polar molecule, have charged ends. The hydrogens are positively charged, the oxygens are negatively charged, which are attracted to the charged ions in the crystal, the positive metals and the negative nonmetals.
So here's an example of what sodium chloride looks like if it was hydrated. You're noticing the yellows and greens represent your sodiums and your chlorines, and the little water molecules are just trapped in between the lattice structure of this crystal. This is an example of how it would look on a molecular level of a hydrated compound. So a hydrate, ionic compounds that contain a specific amount of water molecules stuck in their crystal lattice. Think about it as food stuck in between teeth. Whenever you see anything that is hydrated, you'll notice that it will have an ionic compound followed by a bold dot. That dot is the symbol for a hydrate, followed by a certain amount of water molecules. So if you look below, we can see 3 different examples. We have copper sulfate pentahydrate. That means you have 5 water molecules that are attached to one copper sulfate compound. Next, we have barium chloride dihydrate, which means you have 2 water molecules attached to one of your barium chloride compounds. And finally, we have sodium carbonate decahydrate, which means you have 10 water molecules attached to one sodium carbonate compound.
Now, remember, a hydrate is just a crystal, so it's a solid crystal. Trapped inside of it is water. It does not look wet. It's not a liquid phase. It is a solid crystal.
So if you look at the picture on our left, we're noticing that we have a white and a blue powder. These are both examples of what copper sulfate looks like. As Ms. Diamantopoulos just said, they're both solids. Only the blue is going to represent our hydrated copper sulfate, which means that the crystals have some water to them. Because there's a little bit of water mixed with a transition metal, but still a crystal, they appear blue. However, the anhydrous copper sulfate, which contains no water, when all that water has been removed from it through the act of evaporation, it is a white powder. The same thing goes in the top right-hand corners. If you notice in the top right, that dark blue, cobalt-2 chloride, that is anhydrous. It's completely bone dry. But if you were to add a little bit of water into this mixture, you will get cobalt-2 chloride hexahydrate. And you're noticing that there's a giant difference in the colors.
So when we name hydrates, you're going to combine the ionic and the covalent name. So if you remember, just name the metal, name the nonmetal with the ID ending. And then for the hydrate, as you heard Mr. Schoner say earlier, you're going to use those prefixes to tell us the number of water molecules you have, and then you just say water. So earlier we said copper sulfate pentahydrate, which means 5 waters.
So let's try these 6 different examples. All you have to do is just name the ionic compound and then follow it up with how many water molecules there are. So in our first example, we have copper mixed with a sulfate polyatomic ion, and there are 5 waters. So we can call this copper sulfate pentahydrate. Penta means 5. For the second example, we have lithium chloride monohydrate. For the third example, we have barium chloride dihydrate. For the fourth, we have magnesium sulfate heptahydrate. For the fifth, we have sodium carbonate decahydrate. And for the last one, we have strontium nitrate tetrahydrate. Remember, you need to understand what these prefixes are for the quantities of water molecules in these hydrates.
And it's really important to identify how many hydrates go into those crystal lattices. So whenever heat is applied to hydrates, the water will always evaporate, leaving a sample anhydrous, so again, without water. Evaporation will decrease the mass of the ionic hydrate. Difference in hydrate to anhydrous mass would be the mass of the water which was evaporated out. So here's an example. On the left picture, you see a hydrated copper sulfate crystal. You have 134 grams of it, and we put it on a hot plate at 105 degrees Celsius until its mass remained constant at 109.7 grams. We want to know what is the mass of the water that was removed to make it that white crystal on the right. So you take the original sample, which is 134, subtract 109.7 grams, and you end up with 24.3 grams of water that was removed during the heating process.
We'll know that water is being removed because, as you see in the pictures, the crystal changes color. As it goes from that nice hydrated blue, it becomes anhydrous and turns white. That is a visual representation of water being removed. So to figure out the percent of water in a hydrate, it's ideal and identical that we use the exact same formula from the second lesson of this unit, which is the percent composition formula. The very first thing we have to do in figuring out the percent of a hydrate is calculate the gram formula mass of the entire thing. So for example, this means that you have to add the GFM of the ionic compound and the GFM of the water molecules. If you have multiple, you're going to need multiple amounts of the water.
So if it's pentahydrate, you would do 5 times whatever the GFM of water is.
Then we have to use the percent composition formula to solve, which means that if you're doing the percent composition of water, you're going to put the gram formula mass of all your water from the formula over the gram formula mass of the entire hydrate. That is ionic and water at once. And again, when you do that division, you're then multiplying your answer by 100 to get a percent.
Remember, part over whole.
In this problem, we're also noticing that we don't have any exact compounds. So in the beginning, it says a hydrate that has a mass of 45.3. That's going to be our whole. That's going to be our entire hydrated compound. However, when our substance turns anhydrous at 39.8 grams, the difference between the only 2 grams that we give you can be determined to figure out how much water is being removed, which is our part. So if you take 45.3 and you subtract 39.8, you should get 5.5 grams. So 5.5 grams over our total, which is 45.3 grams, multiply that by 100, then you should notice that about 12% of the compound was lost in the dehydrating process in the oven as water.
These are just 2 different ways to calculate the percent of the hydrate. So either they're going to give you the entire formula, which we said earlier, or they're going to give you the masses of the actual hydrate and the actual anhydrate.
And again, it's just part over whole times 100.
So let's find the percentage by mass of water in lithium chloride monohydrate. So remember, step 1 is to write the hydrate formula. So we have lithium chloride, which is LiCl, the big dot, which represents the hydrate, and monohydrate, which means we only have 1 water. Next, we're going to find the GFM of the entire hydrate. So find the GFM of the lithium chloride and the 1 water molecule. It comes out to be 60.4 grams. Step 3 is to find the GFM of only the water. So it's 2 hydrogens and 1 oxygen, so that's 18 grams. And then plug everything into our table T formula for percent composition. So 18 divided by 60.4 times 100, and that's going to give us 29.8% water by mass in lithium chloride monohydrate.
Let's try another example. It says, what is the percentage by mass of water in sodium carbonate decahydrate? So the first thing we have to do is write down what is the hydrate formula. The reason why we do this is so we can figure out how many water molecules we have. So we get the formula Na2CO3, then the hydrate symbol, followed by 10H2O. The next thing we have to do is find the GFM of the entire compound. So we have 2 sodiums plus 1 carbon plus 3 oxygens plus 20 hydrogens and 10 oxygens. And that comes out to 286.0 grams.
Why do we have 20 hydrogens and 10 oxygens?
Well, if you look at 10 moles of water, it's 10 times 2, and that means you have 20 hydrogens. In 1 mole, there are 2 hydrogens, but in 10 moles, you're going to have 20 hydrogens.
Got it.
The third step is find the GFM of only the water. So that means you're taking 20 hydrogens and 10 oxygens, and that means you get 180 grams. Again, you're using the percent composition formula, and you're doing 180 over 286, multiplying that answer by 100, and you would notice about 62.94% water by mass.